Let's start now. Good afternoon to the members of SSFS, colleagues and friends. I'm Dr. Teh Ziong from the Singapore Institute of Technology, and I will be the moderator for the webinar today. So this is our first live webinar organized by the Society. And today we have Mr. Giulio Gennaro from Core Power UK to address an interesting topic, which is on the future of nuclear power with focus on the molten salt reactor for ocean transportations and also concern on the marine installation. So before we begin our webinar, I would like to remind everyone to mute your microphone at all time, and all the questions to the speaker should be posted in the chat group, and the speaker will be addressing the questions and comments at the end of the talk. So this webinar will be recorded. Our webinar will begin with the opening speech from our newly elected president, Mr. Prem Shankar, followed by the talk from Mr. Gennaro, and our speaker will be taking some of the questions from the audience at the end of his presentation. So without much further ado, I'd like to invite the president of SFSS, Mr. Prem Shankar, to give his opening speech. Mr. Shankar, please.
Thanks, Ian. Should we wait for a while more because people are joining? I can still see many people joining, so maybe we can wait for 2 more minutes.
All right, sure, yeah.
Yeah, okay, great.
Shall we just start now, Prem?
Yes, I think we can start now.
Right, okay.
Right.
Please.
Okay, good afternoon, everyone. On behalf of the Society of Floating Solutions Singapore, I'm pleased to welcome you all to the first webinar of our society after the new council took office in October. At the outset, let me thank the Technology Committee of SFSS comprising Dr. Ziang and Professor Alan Maggie, and together with Ivan Stoichev from the Social Committee to have worked with promptness and diligence to make this webinar a reality. Another word of thanks goes to Iris Kim, a member of SFSS, for her help in creating the webinar materials and flyers. Thanks, Iris. One of the objectives of SFSS as a society is the dissemination of knowledge and for educating our members, the industry, and the society at large about the possibilities that floating solutions bring to the table for the modern challenges that our society is facing. And energy production and storage is one such challenge. Whenever there is a talk of nuclear energy as a viable clean energy option, it is almost always met with raised eyebrows and skepticism, fueled by the unpleasant experiences the world has had with them before. However, The domain of nuclear technology is undergoing rapid transformation with highly safer, compact, and much easily deployable technologies being developed. We may not be aware of it, but a lot is going on. And there's every possibility of a safe mass production solution being developed over the next decade. One such technology is the molten salt reactor, or the MSR, which does away with the traditional solid fuel rods used in pressurized nuclear reactors, and it instead uses chloride or fluoride salt infused with fissile material, claiming to make the technology much more compact and safer. One company which is pursuing this approach for the shipping industry is Core Power, which is currently developing its own m-MSR, which is the marine MSR, which stands for Marine Molten Salt Reactor, an application being developed for powering ships so we can have cleaner oceans in the future. So Core Power recently raised a round of funding with Bill Gates being one of the investors. So today, I am pleased to welcome Mr. Giulio Gennaro, the Technical Director of Core Power, and he's also a member of Society of Floating Solutions Singapore. And he's going to talk about this new technology and its possibilities. Giulio is an Italian chartered mechanical engineer, graduated from the University of Genoa, Italy, with more than 20 years of very diversified experience in the maritime industry. He has been a class surveyor, failure investigator, engineering consultant, and technical director. He has always been interested in ways to raise ship propulsion efficiency and to reduce total life cycle costs and externalities. He started his career developing expertise related to machinery, especially diesel engines. From there, he moved to ship propulsion and then to energy efficiency for propellers and propulsion improvement devices, total life cycle optimization, asset integrity, and asset management. Since 2017, he has been engaged in reviewing and evaluating alternatives for shipping decarbonization and started considering m-MSRs as the dominant option to achieve it. He started cooperating with Core Power in 2018, firstly as an external consultant and currently as a technical director. So I hope we are going to have a very educative session and a lively interaction from our attendees. Over to you, Giulio. Thank you.
Thank you, Prem. Good afternoon, everybody from Singapore. So we will be talking about molten salt reactors, a clean, safe, and affordable power for marine installation. So we know that maritime operation must be decarbonized as for IMO, unanimous approval by all 174 countries. Shipping must decrease greenhouse gases emissions by 50% in respect to 2008 basis. This effectively means that more than 60,000 cargo ships must reduce emission by about 90% by 2050. And this is a huge challenge. However, this is not enough. We cannot consider only direct CO2 emissions or greenhouse gas emissions. We also need to consider, together with climate change relevant emissions, also health, safety, and environmental related emissions. We must not displace emission from ship to shore, where they are worst in their effect. So we need to consider not only direct emissions, but also indirect emissions in the total life cycle approach. We also need clear metrics to compare technologies that have a different mix of emissions. If we don't know which is better and which is worse between 1 ton of CO2, 1 ton of SOx, or 1 ton of NOx or particulate matter, we cannot decide about which technology we should foster and which technology we should abandon. Now, the way forward, and not only for shipping, is just to look beyond pure compliance and find future-proof technology that are able to take us deep into the future, Like in shipping, we did a transition from sail to steam, from steam to diesel engines, and now it's time to find a new technology for the centuries to come. A technology where zero emissions or close to zero emissions come as a standard. Now, in order to understand what technology is best, we need to understand also what is really sustainable. Now, sustainability is bound to three necessary conditions. In order to be sustainable, we need to be safe, both in standard operation and in accident conditions. We need to be affordable. If a solution is not affordable, we cannot implement it, so it's not feasible. And also very important, a solution needs to be scaled to the size of the problem. Otherwise, it's not relevant to the problem. The best solution of the world that can take into account that they can solve only a limited part of the problem is not a solution for the problem. And in shipping alone, the size of the challenge is around 350 million tons of heavy fuel oil equivalent that are used every year. So how do we select the best ship, or let's say the best propulsion plant, the best power plant? Usually traditionally in shipping, we have been based decision on the lowest capex, what cost the less to be purchased or to be built. But as we perfectly know, this is not a very good idea, because what is cheap to buy is generally very expensive to be maintained and operated. A better solution is to consider what costs the less as far as private costs, so capex and opex, capital cost and operating cost. This is a better strategy, but it still disregards the emissions and the pollution, so the consequences of what we do toward the society. So actually, the best overall decision, the best overall option is the one with the lowest total life cycle cost, meaning the lowest summation of capital cost, operating cost, and total life cycle externalities, meaning the outcome, the results of the pollution, in case of, let's say, powering, basically externalities are the pollution that are incurred, that are generated during the construction of the asset, the operation of the asset, the decommissioning of the asset, and also along the entire fuel and energy supply chain. If we don't consider the entire life cycle, but we focus only on what comes out of the funnel of the ship, we risk displacing emissions from ship to shore instead of removing emissions. And we introduce a big bias in our decision. Now, as I will explain you in the course of this presentation, the most sustainable option for the powering of maritime assets going forward will be molten salt reactors. Molten salt reactors were successfully tested in the 60s. They are fueled by a liquid fuel instead of a solid fuel, and the fuel also acts as a coolant. They are high temperature, low pressure machines. They can be fueled for life using high assay, low enriched uranium, HALEU, and they are excellent at load following. They are not subject to memory effect or xenon poisoning. That is an issue for a lot of, let's say, for pressurized water reactor, that makes them suitable to be operated for, let's say, base load generation and not for a constantly changing load as it happens for maritime assets. Now, how is the scheme of a molten salt reactor power plant? We have a core with the reactor, and we have a drain tank. The drain tank is a passive safety feature And in case of any issue, since the fuel is liquid, it can be automatically drained in the drain tank, killing the reactivity and killing criticality. Then we have an intermediate loop that takes the heat from the reactor and it transfers the heat to a power conversion system. And in our case, the power conversion system is a supercritical CO2 closed cycle Brighton cycle. Okay, and then of course we have a cooling system, which is very important because when we operate on ships diesel engine plant, most of the heat is rejected to the atmosphere through exhaust gases. In a closed system like this, we don't have exhaust, and in order to reject the heat, we need a much more powerful cooling system. So this is a scheme of the molten chloride fast reactor that is being developed by TerraPower. It's a very simple machine. In the middle of the machine, we just have, let's say, like a cauldron, like a volume, which is filled with molten salts that are infused with the fissile material. Around it, we have neutron reflectors, and then around outside these neutron reflectors, and we have heat exchangers. Okay, so as you can see, it's basically a very compact cauldron. Okay, if we go and look at the power conversion system, it's basically a gas turbine, a closed cycle gas turbines. We operating on supercritical CO2. That means CO2 at a pressure above about 7 bars and with a temperature above 33 degrees. And in these conditions, CO2 behaves like a liquid when I compress it, and it behaves like a gas when I expand it. So I have very good expansion work that I can extract from the turbine, and I have very little compression work that is required in the compressor. So basically, in order to maximize the efficiency of the cycle, we have two recuperators. We recuperate the heat of the flow that comes out of the turbine, and we exchange the heat with the cold gases before they enter the heat exchanger. And then we have another recuperator, a low temperature recuperator, that also is used for the similar purpose. That means that we reject heat at very low temperature, below 70s or 60 degrees, down to about 27 degrees. Since we reject heat at such a low temperature, we no longer need additional, let's say, heat rejection, waste heat rejection recovery system, and we can maximize the efficiency of the plant. So if we compare molten salt reactors and pressurized water reactor, the biggest differences are the following ones. First of all, as we said, the fuel is liquid instead of being solid. That allows a passive walkaway safety, which is very important, especially if we want to deploy this type of reactors in commercial shipping and in maritime, let's say, structures. And the fuel also acts as a coolant. So if I lose the coolant, I also lose the fuel. That means that I lose criticality. In addition, the fact that the fuel is liquid instead of being solid means that I can easily reprocess the fuel. And this means that for the same amount of energy, I have a much less spent fuel, about 95% less spent fuel in respect to a pressurized water reactors, where spent fuel is not basically reprocessed because uranium costs very little, and reprocessing solid fuel is quite a feat. Another big difference is that we operate at ambient pressure instead of operating at high pressure. So basically, it's like comparing a pressure cooker with the saucepan. If you operate a pressure cooker, if you have an overpressure, it might explode and you might have parts, flying around. So if we have an explosion of a pressurized water reactor, like happened in Chernobyl or Fukushima, that were not nuclear explosion, but still we have a large contaminated area. Instead, an MSR is like, let's say, using a saucepan. If I have a problem, I have a leakage. I don't have an explosion. And I have a leakage in the immediate vicinity of the reactor. So 2 meters, 3 meters around the reactor, not kilometers. In addition, since we operate at high temperature, we can be much more efficient. A supercritical CO2 Brighton recuperative cycle can reach and even go beyond 45% thermal efficiency, while a steam ranking cycle has about 35% thermal efficiency. So we can achieve a 30% increase in efficiency, meaning that for the same energy that we can produce, we can have much lower CapEx, much lower OpEx, lower externalities, and we use less natural resources. Also, molten salt reactors are self-stabilizing, while pressurized water reactors are basically inherently unstable. In addition, molten salt reactors are very good at load following, like pressurized water reactor basically prefer working at a fixed working point, generating base load. So we can have a compact machine, cheaper, that can be adapted to electric propulsion, electric generator, create industrial heat, and also operate as energy storage, thanks to the molten salt. So we did several calculations, total life cycle calculation, to assess private cost and external cost for a different range of ships. So this type of reactors is very apt to be installed on high power ships, so medium to large ships. In this case, we are considering a 14,000 TEU post-Panamax container ship, and we can see that on the left, we can compare heavy fuel oil, low sulfur fuel oil, scrubber, and LNG, either low pressure or high pressure. And we can see that in principle, moving to LNG allows a reduction in operating cost and a reduction in externalities, both health, safety, and environmental externality and climate change externality, and a slight increase in capital cost. However, LNG is still not compatible with IMO 2050 goals. So we need to transition to green fuels. So the next two columns are green ammonia and green methanol used in internal combustion engine. As we can see, the CapEx, which is the light blue bar, is still fairly low, but the operating cost, which is the dark blue bar, shoots up. We have a dramatic increase, more than twice, of operating cost. At the same time, we have a slight reduction in externalities, both health, safety, and environmental and climate change. If instead of using internal combustion engine, we use fuel cells, we witness not only a sharp increase in operating cost, but also a sharp increase in capital cost and a further reduction in externalities. But still, the cost for operating ships on internal combustion engine or on fuel cells and green fuel will be huge. Instead, if we consider operations with molten salt reactors, we see that we have a quite large increase in capital cost, but we have a drastic decrease in operating cost, and at the same time, externalities are minimized. So as we have seen, molten salt reactor for large ships guarantee superior economics. They guarantee the lowest private cost. They guarantee the lowest externalities. That means the lowest total life cycle cost, without pushing emission from ship to shore and without needing large infrastructures, because once I install on the ship a reactor that it's fueled for life, I only need to, let's say, decommission the reactor at the decommissioning of the ship. There will be no longer the need to provide tons and tons and tons of fuel produced and shipped around the world. Of course, we have the issue of the capex, because shipping in particular is used to a low capex, high opex scenario, while this is the opposite. And this can be solved through leasing. So basically, the manufacturer of the reactor will lease through a power purchase agreement the reactor to the ship owner. The manufacturer will still be the licensed operator of the reactor, and he will be responsible for the through life maintenance, the crewing of the reactor, and also the decommissioning of the reactor. Because it's very unlikely that ship owners or other operators want to become a licensed nuclear operators. Now, what is the impact on shipping? So this will be all electric ship, as close to zero emissions as possible. They will enjoy competitive advantage. And as we said, we are talking about medium to large ships. They will be cheaper, they will be faster possibly, more profitable, and they will not be subject to fuel cost volatility. At the same time, smaller ships, we will not be able to install this type of machinery, or ships that will opt not to install this type of machinery will need to use either green electrofuels or fossil fuels and derivatives. So they will be subject to higher cost, either because green electrofuels will be very expensive, or because they will be subject to a high carbon taxation. But this does not stop to ships. So there are large opportunities to power floating plants with this type of technology. So the first things that we can consider is floating plants to produce zero carbon fuels. But we can also consider floating water desalination plant. We know that fresh water is becoming more and more of a needed commodity. We can also consider floating electric power plants. Russians have already, let's say, commissioned nuclear floating plants. Chinese are working on it. South Koreans are working on it. But they are considering all the, let's say, standard pressurized water reactors. Using molten salt reactor would introduce further advantages. We can also consider the oil and gas industries that also needs to decarbonize. Even if we transition to a society where fuel will no longer be, fossil fuels will no longer be used, we will still need petrochemical products. So we will still have an oil and gas industry, and we could power FPSOs with this technology. We can also consider floating data centers, floating processing plant, floating recycling plant. And why we are considering floating installations? Because the main and possibly the only drawback of nuclear power is the need for a heat sink to reject the heat. And if we put a nuclear power on land, we need to use basically fresh water. Instead, if we put it on sea, we assess an infinite heat sink, which is the sea, and we no longer have this problem, and we increase safety very much. Now, there is a lot of talk about using variable renewable energies to produce electro-green fuels. However, the problem is that variable renewable energy sources cannot power an industrial process 24 hours a day, 365 days a year, due to the fact that they produce erratic power, and they have a low capacity factor. So let's check a couple of numbers to understand how big is the problem. So we can use data from the International Energy Association and from the US Department of Energy that we have rearranged a little bit to consider molten salt reactors. Okay, so basically, let's start with capacity factor. The capacity factor is how much energy we generate in respect to what we could theoretically generate running the plant at 100% power 100% of the time. So we see that the capacity factor of variable renewable energy is quite low, from 29% for solar, 40% onshore wind, 44% offshore wind, and these are average numbers. Of course, best in class can be more than this, but if we need to consider a widespread application, we need to consider average. While for nuclear power, the capacity factor is in excess of 90%. Now, if we consider the total cost of the energy, LCOE, we can see that solar and onshore wind are quite cheap. Offshore wind, on the contrary, regardless what we hear, and according to official documents, it's quite expensive. While MSR, since there will be, let's say, 30% more efficient than pressurized water reactor, are not super cheap, but quite affordable. The difference is that while molten salt reactors are fully dispatchable, so they produce energy in the quantity that we need and when we need it, variable renewable energy sources are not dispatchable. So they produce energy when they can and for the quantity that they can. So not only we need to have an excess installed capacity to produce the energy that we want, but we also need storage because we want the energy to be available when we want it, not when it can be available. So we need to add to the cost of variable renewable energy the cost of the storage to make the power supply secure. So let us consider hydropower as a storage, because it's the cleanest form of storage that we can have. And if we do this, we find out that the total LCOE of the power generation plus the storage for variable renewable energy shoots up, okay? And it becomes, in the best case scenario, almost twice of the cost of MSR. And then if we also consider the resources as far as raw material, let's say cement, steel, glass, that are needed to implement this massive deployment of variable renewable energy, and we compare it to what is needed to molten salt reactors, we go from, let's say, 500 tons of materials per terawatt hour to more than 22,000. So we all would like to have free, cheap, let's say clean and green power, but sometimes physics gets in the way. Now let's apply the above to Singapore. We know that Singapore is one of the most important bunkering ports in the world. In 2018, about 50 million tons of bunker were sold in Singapore. And due to the, let's say, lower energy density of zero carbon fuels, these 50 million tons of fossil fuel are equivalent to about 100 million tons of zero carbon fuels, like green ammonia or green methanol. Let's suppose that in the future, 30% of this quota will be zero carbon. That means that we need to produce and sell in Singapore about 30 million tons of zero carbon fuel per year. It's a large quantity. Now, the energy that is required to produce 1 ton of zero carbon fuel is about 10 megawatt per hour. That means that the energy that we need to create 30 million tons is 300 terawatt hours, which is equivalent to 34 gigawatt of new clean power capacity, rated power capacity. Now, let us compare it to the existing power generation in Singapore, which is black because it's basically based on LNG. We have in Singapore now about 14 gigawatt of installed power capacity. So we need to add 2.5 times the existing one. Okay, so it's not easy. Now, what options do we have? For sure, we don't have wind because we don't have wind in Singapore. Let's consider solar. I mean, somebody would say that solar, due to the raining, the precipitation in Singapore is not optimum. But let's consider solar and compare to MSR. Now, solar, we have, as we have seen in the previous slide, has a capacity factor of about 29%. So in order to have a new clean capacity of 34 gigawatt, I need an installed capacity of 118 gigawatt. Huge. While MSR, considering a 90% capacity factor, would only need 38 gigawatt of installed capacity. But that is not the only difference, because if we use solar, we still be subject to an erratic power production. So we will have a huge footprint, huge resources, and still not have a dispatchable energy. So we also need to install a large storage capacity to govern this erratic energy production. While with an MSR, we would have a smaller footprint, we would need less resources, and we would have a full dispatchable energy that we can control on command. Now, you might have heard about the Advanced Reactor Demonstration Program, ARDP. The US Congress has appropriated a $4 billion budget for the development of advanced reactor, allowing, let's say, 50 to 80% cost share, path to licensing and the use of US national laboratories. And the awards will be announced later this year. So as core power, we have formed a consortium in which there are, let's say, 4 major partners and, let's say, other partners, second-tier partners. And in the 4, let's say, leading partners, we are ones. Then there is TerraPower, which is the nuclear reactor design company, let's say the major shareholder of which is Bill Gates. Southern Company, which is a major utility in United States, and Orano. Orano is a French company manufacturing nuclear fuel. Then we have several, let's say, second-tier company, and it's a little bit funny considering 3M a second-tier company because it's, I mean, one of the most important companies worldwide. Now, the scope of this consortium is to build the first marine molten salt reactor based on TerraPower molten chloride fast reactor. The role of core power in this consortium is, of course, to co-fund the research and development, and also to lead the work to marinization of the molten chloride fast reactor, because we perfectly know that what works at sea works on land, but the opposite is seldom the case. So if we want to use this technology at sea, we need to be sure that it's designed to be operated at sea from the beginning. And then the second step will be develop mass manufacturing of molten salt reactors, because let's say that we have about 20,000 ships that are eligible size-wise for installation of molten salt reactors. So considering the life cycle of a ship is around 20 to 25 years, that means little less than 1,000 ships per year. And considering multiple reactors, you can really understand that this is the first time that we can consider mass manufacturing of nuclear reactors, while before we were only considering manufacturing of very large reactors, but very few of them. So the economics related to this technology, once it will be applied to shipping and to maritime installation, will change completely. And Core Power is also building, let's say, the integrated power system for molten salt reactors, because we need to run, monitor, control, and operate the reactors. Another important aspect is regulatory approval. So we are, let's say, liaising with important flag states, in particular UK and US, to champion the introduction and the amendments of regulations about nuclear power in IMO. IMO already consider in SOLAS nuclear power, in particular regulation A49112 is the code of safety for nuclear cargo ships, but it refers to old pressurized water reactor, so it needs to be amended. We are also cooperating with classification societies, and we aim for an approval in principle by around 2024. And we are also cooperating with the International Atomic Energy Association via our advisory board members. So the conclusions are that in the path to the decarbonization, IMO 2050 is not enough. Molten salt reactor going forward will be the dominant solution for marine power, being safe, clean, cheap, and abundant. They will create a platform with a new competitive advantage for ships that will be able to install them, and that it will take us deep into the future in the powering of maritime assets. MSR are being developed as we speak. We have a roadmap in order to do it, and we can do it within IMO 2050 timescale. However, maritime industry must be proactive in this transition and must engage in this tradition. While it is true that, let's say, investing in a new technology being developed might be risky, we have also seen that not investing in this technology, but relying on the technology that are being proposed today, and in particular green fuel, will be extremely costly. So maritime industry engaging in development of molten salt reactor is a proactive engagement that will lead to a de-risking of maritime operation. Finally, there are recommendations. So in particular, IMO should abandon piecemeal regulations with threshold on individual emissions. The reason is very simple. Suppose that we have two technologies. One technology that emits at 99% of all the thresholds, and this technology is compliant. And then we have a second technology that emits at 0% of all the thresholds but one, and for that only thresholds, it emits at 101%. Now, the second technology is clearly superior to the first, but the first is compliant and the second is non-compliant. So with regulations that have thresholds on individual emissions, we are not able to foster the best technology. So we must abandon this type of regulation in favor of a total life cycle emission regulation that consider both direct ship emissions and indirect ship emissions. In addition, we need to move from an emission approach to an externality approach in order to be able fully to compare different technologies with different mix of emissions. And the only way to compare different mix of emissions is to quantify the dollar value of the externality, to quantify the damage that this pollution creates to the mankind, to the environment, to the biodiversity, and to the climate. And finally, key flag state should lead the updating of the rule for atomic ships and in fostering the adoption in IMO of better regulations. So we must decarbonize, and Narcos did it already, so why cannot we do it? This is an electric submarine that was discovered a few weeks ago in Colombia. So thank you very much for your attention. I will be happy to take any questions you might have, and I invite you to register at our website for more information and updates on marine molten salt reactors. Thank you very much.
Thank you, Giulio, for the interesting presentation. Okay, we have a few questions from the audience. Okay, the first one from Ryan. So Ryan was asking, how often does the m-MSR fuel need to be processed to remove the fission products? And also, since the liquid fuel is easily reprocessed, how is it non-proliferation ensured? Okay,
so basically we aim to produce sealed reactors that are fueled for life. So basically ships will be built without the reactors in a conventional shipyard. They will go to a nuclear reactor, to a nuclear shipyard where the reactor will be installed. Then they will be operated for the entire lifetime. And when the time to, let's say, decommission the ship comes, the ship will go back to a nuclear reactor. The reactor will be extracted, removed from the vessel. The vessel will become, let's say, cold, and will go to a scrapyard to be scrapped and decommissioned. The reactor will be drained. The fuel, the total fuel will be taken out, and the spent part of the fuel will be separated from the, let's say, still good part of the fuel, because we know that in a reactor, we use basically less than 5% of the fuel. Okay? So this is, this is the idea about the fueling. In respect of, let's say, the proliferation, we will not have any handling of fuel, either fresh fuel or spent fuel, outside, let's say, approved nuclear facilities at during the construction of the vessel and the commissioning and the decommissioning. And absolutely no possibility of, let's say, touching or using the fuel during the life of the vessels. So the reactor will be sealed and will be the reactor compartment totally inaccessible. Okay.
All right, thank you. We have one question from WCH017 asking about what happens to this fuel reactor when it comes to ship recycling.
Yeah, okay. So as we said, when the ship, what is important is that the owner of the reactor and the subject responsible for the reactor will not be the owner of the ship, but will still be the maker, okay, through the leasing scheme that we have seen. So when the ship ends its life cycle and needs to be scrapped, the reactors will be extracted and will be decommissioned by the reactor manufacturer, okay?
All right, thank you. Okay, one question from Alex Ng. What are some of the special requirements for commercial ports to be able to receive such nuclear-powered vessels? And how many ports in the world are ready for this technology in terms of technology, regulatory, security, and safety?
Okay, so we should recall that the first nuclear cargo ship, nuclear ship Savannah, touched around like 74 ports worldwide, if I remember correctly. And she was visited by about 1.4 million people. So it has been done in the past. It can be done again today. It will not happen overnight. And this is part of the regulatory process that we will be going through starting this January. the very important difference between a molten salt reactor and a pressurized water reactor is that in case of an issue to a molten salt reactor, we have a leakage from the reactor that will be, let's say, within the, how you say, the shield, within the containment. We cannot have an explosion and a dispersion of radioactive material kilometers from the ship, okay? So basically, one of these ships will be self-enclosed also in respect to, let's say, the safety issues. We don't expect these ships to be able to trade immediately worldwide. The first deployment of these ships will be most likely on a fixed route. So in this last slide, I don't know if you can see it, we have a pre-design of a 390,000 deadweight tons, very large ore carrier. So we expect that this type of technology will initially be deployed on vessels like this, trading back and forth to ports always on the same route. And as the technology, I mean, the political, let's say, bodies, the regulating bodies and the ports will see the benefit of this technology, the number of ports that will be able, that will allow this type of ship to operate will increase. But this is definitely a part of our, let's say, regulatory roadmap in the months to come.
All right, thank you. So in terms of this, any special infrastructures that is required to host this type of nuclear powered vessel?
Not really. So let's say that there will be a change in the way ships are built. So there will be, we envision some, let's say, nuclear shipyards where the reactors will be produced and installed on ships, while the hull themselves will be more economically and efficiently built in, let's say, a conventional shipyard, but without the reactor part.
All right, thank you. So one question from Rajiv. What is the smallest economical size of MSR in terms of power output?
Okay, so let's consider that one of the biggest, let's say, cost in nuclear power is licensing a new type of reactor. So we cannot consider having a large number of different reactors. What we consider is having, let's say, a modular fleet, a modular size of reactor. And we are considering the module about 8 to 10 megawatt electric. So given the energy requirement of the vessel, meaning the average power required across the lifetime of the vessel, we will install 1, 2, 3, 4, 5, or maybe more reactors, okay? In steps.
All right, thank you. So talking about lifetime, what is the lifetime of such a vessel?
Well, I mean, usually lifetime of tankers is around 20 years. Lifetimes of bulkers and other ships is around, let's say, 25. And the lifetime of, let's say, Ro-Ros and, let's say, cruise vessel can be longer than 30 years. So the idea is to have reactors that are designed and fueled for a lifetime of at least 30 years. And then in respect to the vessel and to the power, we can play around. So there is a difference between, let's say, a diesel engine and a reactor, because a diesel engine, let's say, has a maximum continuous rating that you cannot overshoot unless like 10% for a small amount of time, according to regulations. While a nuclear reactor, you can, let's say, play with the life and the power and use it at higher power for a shorter amount of time or a lower power at a longer amount of time. There is a latitude in this.
All right, thank you. Okay, so what are the sort of maintenance that's required for these reactors? This is asked by Bushan.
Okay, so basically the plant will be divided into very different parts. So the reactor itself and the power conversion system. The power conversion system will be as we said, supercritical CO2 turbines that will be basically maintained like any other gas turbines. The reactor itself will be a passive system, so basically with no moving parts inside. So we expect very little maintenance, if any, for the reactor. Okay, so it will be just a generator of heat with a heat exchanger and a convection flow inside the reactor itself.
All right. So the MSR will have a higher capex, and Anis Hussein was asking, why is this capex in order of magnitude more than almost 10 times based on the cost comparison, which is more than the internal combustion engine?
Also, we cannot do a direct comparison of CAPEX and OPEX. We need to do a total life cycle approach comparison. Also, due to the fact that diesel engine has a fixed power, while a molten salt reactor can be operated with, let's say, a latitude of power. But we consider that around the 10 megawatt reactor could have a cost of around $50 million US. But again, it's very misleading to reason in terms of capex and opex instead of in terms of total life cycle.
Okay, thank you. All right, in terms of risks, Peter was asking, what are the risks, say, in collisions or grounding that distort the reactor?
Can you repeat, please?
What are the risks in collisions or grounding that will distort the reactor?
Okay, so as we said, there is already a regulation in place, Resolution A491 of IMO, that prescribes the requirements of a nuclear cargo ship in respect to safety. In particular, the reactor must sit well within the hull, deep into the hull, in order not to risk a damage in case of collision and grounding. In addition, these type of reactors can be drained and may become immediately no longer critical. So let's suppose that one MSR vessel grounds and we need to refloat the vessel, or we need to do wreck removal. After the grounding, we have a draining of the reactor. So the reactor is no longer critical. So the salvors can intervene and refloat or remove the ship without having to care about keep providing cooling to a critical reactor. Okay, so we completely decouple the reactor criticality and the reactor safety from the ship safety.
Right. Okay, I hope that answers your questions, Peter. So one question from Krish Naraj. What is the safeguard in the event the reactor cannot be recovered from a sinking ship? Who will be responsible of these consequences?
Okay, so again, the biggest safety feature is the draining. Okay, once the reactor is drained, it's no longer critical. The salts, the molten salts, will solidify and they will stay there. So we already have several pressurized water reactors that were on submarines that sank and now they are at sea. So this will always be the case. So if an MSR ship will sink, there will be no more radioactivity aside from, let's say, the normal, let's say, decay from the, let's say, the fission products, which is rather limited. And the reactor will be self-encased and it will be sitting at the bottom of the sea for ages to come. Okay, but instead, if we have a sinking or a grounding in shallow water and we need to recover, as we were saying before, we can recover it without, let's say, additional risk, because again, the reactor will be drained and so no longer critical.
All right, thank you. Okay, we have two questions from Regina, which is related to the heat reactors from the heat. So is this reactor intended to be used like a boiler or in a conventional steam turbine?
Okay, so as we said, reactors provide heat, and then we need to couple them with the best power conversion system to maximize, let's say, the power conversion efficiency. So we could couple this reactor with a Rankine steam plant, but it would be substandard. The best solution is to couple the reactor with a supercritical CO2 recuperative Brayton cycle, moving from 30 to about 35 to about 45% thermal efficiency. Okay, so basically we have a gas, supercritical CO2, that will go around a closed circuit. It will be compressed, heated, it will expand in the turbine, and it will be cooled. And it will go around in loops in a closed cycle. So no steam generation.
Okay. One question also from Regina is, how do you control the thermal output without any moving parts in the reactor?
Yeah, this is a very good question. So basically, this molten salt reactor try to stay at constant temperature. If I extract more power from the reactor, the reactor tends to cool down, and the reactivity increases, and it outputs more thermal power. On the contrary, if I extract less power from the reactor tends to heat up, the reactivity decreases, and then it puts out a lower thermal output. So basically, by modulating how much heat I extract from the reactor, I can modulate the reactivity and the thermal power output. Okay, so I don't need control rods to stimulate higher or lower reactivity, but I can operate on the cooling, on the intermediate loop of the reactor, okay, accelerating the cooling flow in the intermediate loop or decelerating it, extracting more or less heat, and the reactor will let's say, respond to this.
Okay. All right, thank you. We have two questions from Bushan. The first one is, if the vessel is laid up, then how is the reactor isolated since power is no longer required?
Okay, we can throttle the reactor down to almost, let's say, zero power, okay? And we can decide either to keep it in that way, if it's going to be a long-term, let's say, deactivation, we can drain the reactor, okay? If it's a short-term deactivation, we just can keep the reactor, let's say, running at minimal load. So we will still have to provide minimum cooling to remove, let's say, the decay heat.
All right. Okay. And second questions from Bushan is on the change of CO2 gas that runs through the turbine. Is there a need to change this CO2 gas, or is there any deteriorations of the gas?
No, in principle, no. In principle, it's a sealed system and it's not self-contaminating or anything, okay? So there might be need to, there might be, let's say, some leakage and minimal leakage through the seals, so might be need to top up a little bit over time, but this is, let's say, a very secondary issue. Another thing that I haven't mentioned is that supercritical CO2 gas turbines are also very interesting for, let's say, maritime operation, because they are extremely compact. If we compare a steam turbine to a supercritical CO2 gas turbine, the size of the supercritical CO2 turbine is like 10 times as smaller, okay? So, and with all the consequence also for not only in terms of volume, but also in terms of mass. So this is very interesting for an asset like a ship or a floating structure.
All right, thank you. I have read out all the questions in the chat group. Is there any more questions from the audience? All right, if no, then I would like to thank Mr. Giulio once again to present his talk on this first webinar by the SFSS. Thank you very much. So I would like to thank everyone also to attend this webinar, and please do watch out the Society's webpage for any future activities, which is will be posted in the webpage. So you can visit this Floating Solutions website, or you can scan this QR code to access to the website. Thank you very much, everyone. Thank you, Giulio.
Thank you.
Thank you.
It was a pleasure. Have a nice day ahead. Bye-bye.
Bye-bye.